to get that off. Screen there. All right, yeah. Thank you so much to everyone for coming on this Friday morning slash afternoon for the East Coast crowd. Thanks for to Oben for organizing this month's Slack Talk. I'm very excited to share my work that I've been doing for about the last year or so, looking for data-driven ways to discover so-called novel interactions between chemical species in the atmosphere. Um, oh, hang on. Okay. Yeah, I was bearing the lead a little bit in the dead of last night. My manuscript that this presentation is entirely based on just got published in JGR Machine Learning and Computation. Um, Thank you for all the claps, and thank you for potential people in the Zoom room who like maybe reviewed this paper or at least have seen some preprint of it before yesterday. Yeah, download your free PDF today. But this talk will basically be a pretty good summary of the motivation and results presented in this work. I think a good place to start is a thing that I think a lot of us in this room are aware of, which is that while extensive, our understanding of like a complete understanding and theory of chemical reaction occurring in the atmosphere is incomplete. And this incompleteness stems from, I would say, multiple sources. Um, and these uncertainties, I think, are things that people in the field have known for quite a long time. Almost 20 years ago, a very, very, novel, I would say landmark paper was published on the nature of just how the nature and extent of like how many unknown species there are yet to be discovered in the atmosphere, as well as there being significant uncertainties quantifying reaction extent. This has shown up, at least in my findings, a lot in the RO2 in the peroxy radical secondary organic aerosol literature. There's a lot of uncertainty in how oxidation of gas phase chemistry in the atmosphere leads to these downstream SOA products. There's also, even within these, a more specific thing that I was reading recently from Sarah Murphy was previously, like, peroxy radical, oxidation products previously thought to not be significant enough for consideration in the atmosphere were recently discovered to be actually happening at much larger branching ratios than people thought, much more than zero, that is. And so all of this kind of leads to this effect that this situation we find ourselves in right now, which is we are not only limited in our ability to forecast chemical composition, forward in time, numerically speaking. This also has the effect of, less than fully informed policymaking. This is important because something on the order of 8 million deaths a year can be attributed to poor air quality, deficient air quality. So this is kind of not only from like understanding the completeness of this problem from a science perspective, this is important from a policymaking and kind of environmental and I would say humanitarian point of view. That is not to say that there are no existing discovery methods that are useful. In fact, there are many that exist at both atomic and more kind of bulk chemistry levels they're very, very significant and have shown very useful in getting us our like current understanding of highly complex chemical reaction mechanisms that we have the ability to work with today. I would say a very popular atomic level way of kind of discovering new reactions and really nailing reaction rate constants and reaction extents are structure activity relationships. I would say these have a lot of pros associated with them, namely because these methods range from you can take a purely empirical approach using data, you can take a purely theoretical approach, thinking about potential energy surfaces, things of that nature. But they are still limited in that certain SAR approaches are basically only as good as their data sets. And this method of kind of determining reaction extents can fail or can propagate uncertainties very significantly, even like through with known or not known, rather with what is the word? I would say initial or like primary oxidation pathways that we all know about. Um, this is kind of what I mean when like I say poor OH oxidation representation. And so we might want to look for something different. At if you zoom out to more bulk kinetics, there are other methods that exist in a more data-driven context that can also accomplish reaction discovery. One thing that I have taken a particular interest to are chemical reaction neural networks, originally posed by Ji and Deng in 2021. But what this figure here is showing is a an innovation on this original structure uh, last year that includes mass action and the Arrhenius law to basically provide in concert with atom conservation to come up with these physically consistent atom conserving chemical reaction neural networks that can be used to not only discover the kind of initial connectivity between species in a mechanism in a proposed mechanism, but also can nail down reaction constants as well. The issue with this is that they are necessarily limited to neural networks with exactly one hidden layer, because having more than one hidden layer will kind of break down the chemical and physical consistency introduced into the architecture by Doppler and Pfotzmeier. And they are quite bespoke. And I also know for a fact that certain people in this Zoom room have used these to no avail, porting them from the combustion chemistry context, which these were very initially constructed in, porting them into the atmospheric chemistry space. Um, these have troubles converging with data in our field. So to that end, we wanted to look for something that is we wanted to look for an approach that is data driven, but can circumvent these issues proposed in the last couple of slides. So to that end, we have access to a lot of data. We have a lot of very, very nice chemical forecasting models that we can get a lot of state data from, which means that we don't have to rely as purely on theory, but we also want to leverage our existing process understanding of the reactions that we know about occurring in the atmosphere. The TLDR of this, and what I'll get to later, is that we want to use graphs to model the structure of chemical reaction mechanisms, and we want to use neural networks to kind of leverage the rich data that we have access to in this space. To that end, the method that I have proposed in my recently published work, and also that's kind of the main meat of this talk, is graph neural networks, or GNNs, which are a kind of class of machine learning model architecture to discover new interactions. So with this, we want to leverage, observations. We want to use chemical state data and an existing understanding of how chemistry is explicitly connected in the atmosphere to predict the existence of novel interactions, denoted by this kind of new green arrow here. And I want to start with first kind of a bit of a zoom out and talk about what it means exactly to represent chemical reaction mechanisms or chemical reaction networks as graphs, which I want to look at with just like this two reaction system here, or like I guess 2.5 reaction, because the first reaction does require oxygen. But what I have here is just a very simple two reaction system that starts with oxidation of CO. And this is kind of representing OH recycling and ozone loss that leads from this oxidation, right? You can represent the change in concentration for each species in this two reaction system as a system of differential equations, right? That are based on these two reactions happening above, color-coded rate constants according to which reaction we're dealing with here. And this is very useful, and this is, I would say, to my understanding, how most like numerical forecasting models are actually like used. You have a system of a lot of coupled differential equations, and you are stepping these forward in time with a chemical integrator that you have set to a particular stiffness based on how fast all these reactions are happening. But you can also represent this as a graph shown here, right? What this specifically is showing is a bipartite graph. What that means is we have two disjoint sets of nodes, which are in this case either chemical species denoted in circles or reaction nodes denoted by these colored boxes here that show the reactants on the left side of both of these reactions flowing through the reaction node and out to the reaction's respective products. And already immediately here, at least for me, um, representations like these are much more intuitive. Like you can explicitly see how each species is connected by each reactions. Um, coupled ODEs are very powerful, but I would say chemical coupling is not immediately apparent. Um, and I would say, yeah, that's kind of this is very, very nice. I think an immediate question is, well, this is an equivalent representation. That's great, but like, why is this useful? My case for why graphs are useful is when we want to scale up to, I would say, more realistic representations of atmospheric chemistry, like this behemoth right here. This is not even the biggest one, but um, when we scale up to larger mechanisms or larger representations of atmospheric chemistry, like geoschem, which is what I have here, um, you know, representing chemistry as a graph is important because you cannot just visually inspect. You cannot just it becomes intractable to kind of look at the coupling of chemistry when you're at this like stage, right? So this is nice because the field of graph theory can offer some discrete analytical tools that are very, very helpful in analyzing the structure of large mechanisms like these. Um, and it then becomes easier to kind of compare and contrast mechanisms of this size and then to kind of dig deeper into the meat of exactly how things are connected in these mechanisms. Um, Representing mechanisms as graphs is nothing new. This has been going on for, I would say, at least the last like 2 decades or so, um, and have been implemented to achieve a variety of ends, basically. Liu and Law introduced directed graphs in pursuit of mechanism reduction and did so quite successfully. Um, Silva et al. In 2021 did this intermechanism comparison that I was kind of alluding to in the last slide. Um, and using graph theoretic tools made it very, very easy to kind of come up with some summary statistics of mechanisms of very, very different sizes and complexities. Um, in a way where if you were just looking at a system of equations, the system of coupled differential equations, you might not have immediately found the same similarities or differences that they've found in their results. And then also something that we came out of our group this year is Open worked with our a previous undergrad to then explicitly track the speed of chemical cycling in the atmosphere. This is something that, again, would have been much, much harder to do if we were stuck in ODE world. But since they ported this analysis into like looking at the connectivity of a graph, it really lent itself to kind of being able to track how fast chemistry was cycling in the atmosphere. So that's kind of like the big picture of why do we care about graphs. They're very, very nice tools to represent coupled nonlinear systems of interacting entities like atmospheric chemistry. I want to go into what we use these graphs in the context of, which are what I call directed graph autoencoders. And we use these for actually achieving our atmospheric chemical reaction discovery. And this is figure one of my work. This is kind of the big picture layout of how exactly we use graphs to discover to achieve reaction discovery on a known mechanism. And I just kind of want to spend a few minutes diving into this schematic, and then I'll show you some results from there. So we have this thing that I call a directed graph autoencoder. This autoencoder requires two inputs that I alluded to earlier. We need time series of chemical state data, and we also need a graph structure. We need explicit access to what reactions are happening in a mechanism. How we get this graph structure is we take the connectivity of GeoSchem version 14.0, and we remove edges by entire reactions to arrive at kind of a facsimile of an incomplete understanding of chemistry in the atmosphere. What I mean by entire reaction is that we've moved from a bipartite reaction where we have species nodes here and reaction nodes here, and we move to a unipartite kind of projection of this graph where all of the nodes now are just species and all the edges are connecting reactants to products in a directed fashion. So in this way, we lose kind of explicit reaction level resolution, um, but we can kind of keep track of what edges are occurring in which reaction. So we remove entire reactions, namely species edges that constitute particular reaction. We do this to avoid splitting portions of one reaction between training and validation and test sets, which is kind of basically our way of minimizing data leakage our throughout our training pipeline, essentially. So we have these two inputs. We pass them into our encoding block, which is what I call the graph neural network encoding. And we have these two directed GNN convolutional blocks that are what do our low dimensional embedding of the state data and our uh, graph structure. And that is kind of what these blocks are doing is represented by, I would say, these two monstrosities of update equations here, where we take for every chemical species, let's say V for like a vertex in geoschem, the directed GNN conv produces a source and target low level embedding for each chemical constituent in the atmosphere. And this is kind of the math behind how each species node source and target embedding is updated at each layer. Um, I can go back to this later, but I think what the important part here is that through this encoding mechanism, we get a latent representation of geoschem where each species gets two vectors. They get a source embedding and a target embedding, which quantifies generally how each species behaves, both as a reactant and a product. This is really nice because when I was first starting this, I was kind of pleased that there were a lot of encoding mechanisms that could account for the directionality of edges in a directed network, which is really important when we're looking at chemical interactions. But this is a very nice explicit quantification of species and reactions, or of each species role as a reactant product. We can now use these vectors to predict the existence of unseen edges, right? And how we do that is we pass that through an MLP or multi-layer perceptron, very just simple feed-forward neural network decoder with two fully connected layers that finally outputs a prediction of an existing or predicts the existence of a new edge through a sigmoid layer that can then lead us to our output, which is namely if you were to predict the existence between, you basically take the source embedding of one chemical species and the target embedding of another, pass it through this decoder to then arrive at a probability of basically how likely is a chemical interaction flowing from source one to target two to exist. Um, and as it turns out, our directed graph autoencoder does demonstrate better predictive trade-off compared to other baselines. I'm showing just a comparison between our directed GAE and a kind of more vanilla GAE here. We do have some other baselines that we compare this against, but I would say as far as like kind of a direct ablative study, I think looking at the kind of operator characteristic between these two models is kind of a very good place to start. What we're seeing here are these ROC curves of different estimators, either directed or undirected graph autoencoders, with kind of median ROC curve colored in black, shown here. Basically, for all these gray lines indicate that this is just like an ensemble of a bunch of different models that we trained here and are kind of aggregating performance across all 30 models here. Not only do we have, basically what this is showing can be kind of quantified in like what this AUC value is at the top of each plot. The AUC is the area under the curve being the receiver operator, the ROC curve, which is kind of a measure of like how good our predictive model is. The AUC, I would say intuitively, is kind of the basically like probability of a binary classifier to rank the existence of a true interaction, chemically speaking, higher than ranking a false chemical interaction. Um, that's basically saying like it is better able to, it's more confidently ranking uh, real chemical interactions as being more likely to exist than like unphysical or energetically impossible interactions to exist. Um, I think a good question you might be asking is like, well, where do you get this notion of like false chemistry? And what we did to emulate that is we basically took our GeoSchem adjacency matrix and then did a bunch of random permutations of GeoSchem's connectivity to then come up with kind of a candid pool of fake chemistry that is not actually occurring in the mechanism. What that might look like is, a real edge in our context could be carbon monoxide being oxidized to form CO2. A false edge would be flipping the directionality of CO going to CO2, where CO2 loses an oxygen to go back to carbon monoxide. That's an example of something that is not happening in our atmosphere, at least at this stage in Earth's history. And so basically, we generate a bunch of fake edges, and we basically see after training how, or actually throughout training, how good our classifiers, our autoencoders are at correctly ruling out these negative edges or these false edges rather. So that's kind of what this is showing, right? This is our model is really good at correctly classifying real chemistry as existing and fake chemistry as not being part of the actual mechanism. Um, and one thing that I wanted to investigate further is like, all right, is there any particular kind of type of chemistry that this model of ours is really nailing versus is there anything that it kind of should be better at, but is not? And so that's kind of what I have here, where we've kind of partitioned chemical interactions based on what species are participating in each pairwise interaction. And that's kind of what I have here. And so you can kind of see that you can see that this model is mostly effective in ruling out non-existent interactions. That's kind of what's denoted in the orange distributions here for each particular class of chemistry. Um, you can see like basically what we're looking for is like a very, very high concentration of very low scores in the orange distribution, which is kind of which is, except for oxidants, what we're seeing here. And I'm happy to talk about why I think that's happening and oxidants later. But we can also see that um, how our model is correctly classifying true edges as being like, real chemistry. Although the distribution is kind of it is a little bit more dispersed along this like 0 to 1 interval. You can see that with the exception of like sulfur and certain organics, um, our model is very, very good at correctly predicting extant chemical interactions as being real and therefore being like should be included in this mechanism. Um, yeah, sulfur I would say has a very, very funny distribution. I would say that's mainly because Geoschem does treat gas phase and aerosol phase chemistry kind of disjointly. And when we ran GeoCF to get this chemical state data for this work, or that was used for this work, um, reaction rate constants for aerosol phase chemistry were set to near zero or essentially zero, which I think had the effect of kind of overly antagonizing this directed graph autoencoder in terms of its ability to predict sulfur chemistry. Um, I will kind of leave it there, but basically, and also the edges, there are only about like 30 or so edges involving gas phase sulfur chemistry in this entire mechanism. So this, the sulfur distribution, I would say, has far fewer edges than make up, for example, these nitrogen distributions. Again, happy to talk more about that later. Um, to compare these against some other baselines, here is what the kind of vanilla graph autoencoders distribution looks like, kind of much more pulled to each extreme, as well as another graph-based embedding algorithm, which is called NodeTVEC, kind of also has this uh, bizarre pattern of kind of pulling predictions to like either extremes of the kind of potential scoring window. All of that is to say that our graph autoencoder, our DGA is very good at conservatively scoring fake false chemistry very low and correctly ranking real reactions very highly. Um, yeah, so I would say immediate takeaways are we have this directionally aware graph encoding scheme that leads to a richer low level species representation compared to other more vanilla graph encoding methods. Regular GAEs and Notevec can only give us one low level latent embedding for each chemical species, which then when we're using that in terms of decoding predictions for uh, novel chemical interactions, they kind of are shown to be less powerful and less salient compared to our directionally aware schemes, um, which is great. And to kind of put all of this into perspective, we did perform all of this analysis on kind of like a known mechanism with like artificially removed, randomly removed, I might add, chemical interactions, right? We did this because we want to kind of, we wanted like a known explicit target to shoot for as far as quantifying how good these methods are, um, in terms of like their potential for discovering new chemical interactions. But I think a next step that can really stress test this method in the wild is applying this to real data. Um, for those of you that saw me at AGU last year, I'm kind of in the same place now as I was then. I have not yet gotten my hands on any chamber chemistry data, but that is kind of next up on the docket for me to kind of see how well this kind of directionally aware encoding scheme does in the wild in kind of a more focused context like you would see in chamber chemistry data. We're not looking at 1,000 reactions in any particular chamber run. We might be isolating like, I don't know, a few at a time. So I'm interested to see how it would behave in a different context. Um, yes, there we go. Oh yeah, okay. And then also kind of I wanted to get that out of the way before I got here. Um, this kind of came as a result of basically every time I've presented this work in the past, people have asked me, okay, well, how does your autoencoder perform like as you remove more and more edges from whatever mechanism you're trying to complete? As like for example, um, for context, when we trained our models on the partially complete geoschem mechanism, we only removed 20% of the mechanism's total edges in this unipartite projection. Um, and I basically was like, did a quick stress test yesterday of what does the AUC value look like as a function of percent of removed reactions. So you can kind of see, I would say this is kind of like what I kept telling people I would expect to happen. And so I'm very glad that this curve does not go up. But what you can see here is that AUC does decrease, I don't know, by about 10% as you go from 20% removed reactions to over half of the mechanism removed. Um, which sounds pretty cool. I would say like a, 0.83 AUC when you have removed over half of Geoschem's edges sounds like really, really exciting and like, okay, cool. Like this encoding mechanism can really handle like a largely incomplete mechanism. Um, what I want to caveat this with is I did look at the training versus validation loss plots in concert with kind of each of these percent of removed reactions scenarios. And once you get to 60% removal rates, you just see like massive overfitting. Like the validation loss curve just kind of like, you know, shoots off into space after about like the 100th epoch or whatever. So I would say this is kind of a good diagnostic assessment of how basically like how incomplete can your understanding of a large mechanism be before you start getting really bad predictions. The answer is this is probably a slight over this is probably like an overconfident estimate of how our models would do. What I have not done is compare this against baselines, which I would expect to be, I would say, probably slightly worse. Um, yeah, that's kind of that on that. Before I stop for questions, I wanted to give a quick shout out to my research group over at USC. led by Professor Sam Silva, who I'm sure many of you know. Um, yeah, without them, it would not have been possible for me to complete this work. So thanks for everyone for, letting me bounce ideas off you and show you my, drafts of what was just published over the last like few months. Yeah, thank you, everyone. Thanks for listening. Um, that's all I have. I'm happy to take questions for however long you have them.